Have you ever thought about, why your car's transmission doesn't just turn into a complete pile of scrap metal when you're hitting 70 on the highway?
I mean, we take it completely for granted.
Oh, totally. You just sit there cruising along, maybe sipping your coffee, completely oblivious to the staggering amount of mechanical violence happening right beneath your feet.
Right. People tend to think of gears as these static, boring hunks of metal that just sort of exist inside an engine block.
Yeah.
But the reality of what those pieces of steel endure, the cyclic fatigue, the crushing surface pressure, the searing heat, it is incredibly volatile.
And that is exactly what we are diving into today. We've got a really fascinating stack of sources to explore for this deep dive.
It's a great one.
It is. We are looking at a highly technical engineering lab report detailing a Dante and Ansys 2026 R1 simulation tutorial. But, and this is the fun part, the report is presented almost like an explainer video for a MasterChef cooking show.
Yeah, the cooking analogy really works surprisingly well.
It really does. And our mission today, we are going to treat a car gear like the absolute diva. It is requiring an intense molecular spa day to see exactly how engineers use supercomputers to literally cook up the perfect gear tooth before a single drop of physical steel is ever poured.
Well, we could forgive the spa day phrasing for a moment, because what we are actually doing is dragging this steel through a literal trial by fire in a high-stakes digital kitchen.
Right.
Putting raw, untreated steel into a modern transmission is just a recipe for disaster. It would literally go clunk and shatter into pieces before you even made it out of your driveway. Good enough simply does not cut it.
Okay, let's unpack this, because we are talking about an extreme 5,000 RPM environment here.
Yeah, it's intense.
At 5,000 revolutions per minute, the gears are grinding against each other with just thousands of pounds of force. So to survive that sheer friction without grinding down to a nub, the metal has to be completely transformed at the atomic level.
Exactly.
Yeah.
And transforming metal requires prepping the ingredients first. I mean, you wouldn't walk into a Michelin star kitchen and just start throwing things in an oven, right?
Hopefully.
Right. So our digital kitchen consists of the Ansys 2026 R1 and Dante software. And our prime ingredient is a 3D thermal model of the gear.
Okay.
But simulating the microscopic physics of a massive, complex ring gear under 5,000 RPM stress, it takes an almost incomprehensible amount of computing power. If you try to simulate the entire gear at the atomic level, your supercomputer's going to choke.
Which leads to, honestly, my favorite part of the source material. Instead of simulating the whole gear, the engineers just take a simplified 3-degree slice of it.
Yes.
The explainer video uses a fantastic analogy here. It's exactly like tasting one single slice of pizza to see if the whole pie is good. But I have to ask, are the engineers just being a little lazy to save time?
Oh, I wouldn't call it lazy at all.
No.
No. It is a brilliant piece of computational elegance. A gear is perfectly symmetrical. So by mapping out the thermal stresses and phase changes on a flawless 3-degree geometric slice, they can confidently extrapolate how the entire metal ring will behave.
Oh, I see.
Yeah, it saves days, sometimes even weeks, of computing time while maintaining the absolute fidelity of the physics. But, to get that level of fidelity on our little slice, they have to create a highly detailed digital mesh over the 3D model using a CFD physics preference.
Okay, I want to pause on that term, CFD, because that stands for computational fluid dynamics, right?
It does.
So why are we using a fluid dynamics setting on a solid piece of steel?
Yeah, that is a great question.
Yeah.
You use fluid dynamics because we are about to subject this solid steel to massive shifts in heat and reactive gases.
Okay.
Heat transfers through metal in waves, much like a fluid, and the gases we use in the cooking process, they flow around the gear teeth exactly like a liquid.
That makes total sense.
So to predict how the metal will react, the software just has to understand how those elements wash over the complex geometry of the gear.
Right, so they build this mesh over the 3-degree slice, and they program the software to apply what they call an automatic inflation of exactly 14 microscopic layers on the very surface of the gear.
Right.
But why the hyperfocus on the surface? Shouldn't the entire slice get the same level of digital scrutiny?
Well, the chemistry dictates our digital setup here. The spicy stuff, the carbon we are going to add to our recipe to strengthen the steel, it only penetrates the very surface of the gear.
Just the surface?
Yeah, specifically, it only seeps into the top 2.2 millimeters of the metal.
Wait, 2.2 millimeters is incredibly thin. That's like, what, the thickness of a heavy coin?
Basically, yeah. It is microscopically thin in the grand scheme of an engine block, but that tiny boundary layer is where all the friction happens.
Oh, right, where the teeth touch.
Exactly. It is where the teeth physically grind against one another. So if you don't have a super fine grid, those 14 layers in your simulation tracking the physics inside those specific 2.2 millimeters, your software is basically blind to the most critical part of the process.
Wow.
The core of the gear doesn't need 14 layers because its chemistry isn't changing as radically. You just have to know exactly what is happening right at the skin.
Okay, so our digital kitchen is prepped, the mesh is mapped, it's time to actually start cooking. We move to the first major phase of our extreme engineering process, which is the marinade.
The marinade, yes. The technical term the engineers use for this is low-pressure carburization, or LPC.
Right. So we take this 3-degree slice of steel and we soak it in a carbon-rich environment at a blistering 950 degrees Celsius.
Very hot.
Yeah, and according to the lab report, at that temperature, the steel's molecular structure physically opens up and gets incredibly hungry for carbon. How does solid steel get hungry?
Well, heat changes the very architecture of the metal. At room temperature, iron atoms sit in a tightly packed crystal lattice. But when you crank the heat up to 950 degrees Celsius, the metal starts glowing cherry red. The atoms are vibrating so intensely that the crystal lattice physically expands.
It actually grows.
Yes, it shifts into a phase where there is suddenly physical space or interstitial gaps between the iron atoms. The steel is literally expanding its pores, just waiting for something to fill the gaps.
And the recipe they use in the Dante software to feed that hunger isn't just a massive dump of carbon. The source outlines a very controlled cycle. It's 12 boost steps followed by 12 diffuse steps.
Right.
Why not just blast it with carbon all at once?
Because of the concentration gradient. A boost step violently pumps carbon-rich gas into the furnace, forcing carbon atoms onto the surface of the steel.
Okay, so pushing it in.
Exactly. Those smaller carbon atoms squeeze into the gaps in the expanded iron lattice. But if you just keep boosting, the carbon builds up too thickly on the outside edge and essentially clogs the pores. It won't penetrate deeply.
Ah, so that is where the diffuse step comes in.
Yes. You stop pumping in new carbon gas and just let the extreme heat bake the existing carbon deeper into the metal. The carbon atoms migrate inward, filling the lattice down to that critical 2.2 millimeter depth.
Brought it.
Boost, diffuse, boost, diffuse. You did that 12 times to build the perfect gradient.
So the result of this process is that on the outer skin, the carbon level jumps to over 1%. We get this very high carbon exterior.
That's right.
But this creates a massive contradiction in the design. We are building a hard outer shell, but underneath those 2.2 millimeters, the center of the gear remains raw, low-carbon steel. The video literally refers to it as a soft, chewy center. Wait, wouldn't a chewy gear just melt? Shouldn't we want it to be solid rock all the way through if it's handling 5,000 RPMs?
What's fascinating here is that this contradiction is beautifully by design.
Really?
Yeah. In material science, hardness and brittleness almost always go hand in hand. Think of a glass window. Glass is incredibly hard. You can't easily scratch it, but if you hit it with a hammer, it shatters instantly because it has no ability to flex.
Right, because it can't absorb a shock.
Precisely. A car engine is not applying smooth, polite pressure. It is sending violent, jarring shocks through the transmission every single time you step on the gas or shift gears.
That makes sense.
If the gear was solid, high-carbon rock all the way through to the core, the teeth would just snap clean off under the sheer force of those impacts.
So keeping the center raw and low carbon gives it a totally different mechanical property.
It gives it ductility. The high-carbon outer shell handles the constant abrasive friction of the teeth grinding together without wearing down, but the softer, flexible core acts like a microscopic shock absorber.
Oh, wow.
When the gear takes a violent hit, the chewy center allows the tooth to bend a fraction of a millimeter rather than snapping in half.
So the gear is basically wearing molecular body armor over a flexible, shock-absorbing core. That is incredible.
It really is.
But the marinade is only half the battle.
No.
If we just take this glowing, carbon-packed steel out of the 950-degree oven and leave it sitting on a bench to cool down slowly, all that work is ruined.
Oh, it is entirely ruined. If it cools slowly, the iron lattice slowly contracts. It gently squeezes the carbon atoms back out, or they clump together into these useless deposits.
The structure relaxes.
Right, you have to lock that perfect high-tension structure into place before the metal has time to reorganize itself.
Which brings us to the flash freeze, or high-pressure gas quenching, HPGQ.
Quenching is the crucial moment of truth in metallurgy. You take this blazing hot carbon-soaked gear and you hit it with a violent blast of high-pressure cooling gas.
Gas, not liquid.
Right. We use gas instead of liquid oil or water here to maintain absolute control over the cooling uniformity, which prevents the gear from warping out of shape.
Now, the simulation maps this cooling process out as a rapid, time-varying drop in temperature, and this sudden freeze forces a literal phase transformation in the metal. It's not just dropping in temperature, right? The steel is actually shape-shifting.
Yes.
So when we look at the thermal X-rays from the Ansys software during this flash freeze, what exactly are we seeing?
Well, we are tracking 3 distinct structural phases inside the metal as the temperature plummets. The software tags these different structural states using what they call state variables, or SVRs for short.
Okay, SVRs.
Yeah, they're just how the simulation tracks the shifting phases on a microscopic level. The first one we track is austenite, which the system labels as SVAR21.
And austenite is the hot structure, right? The form the steel naturally takes when it's superheated in the oven.
Yes, that expanded lattice we talked about earlier is austenite. But after the high-pressure gas quench, the thermal X-ray shows the austenite fraction drops to 9.99 times 10 to the negative 7th. Mathematically, that is basically 0.
I have to say, the analogy I thought of for austenite is that it's the ghost phase.
Oh, I like that.
Yeah, it reminds me of a wild party guest who absolutely dominates the room when things are loud and heated, but the exact second someone turns on the AC and the lights come up, they completely leave the building.
That captures the behavior perfectly. Austenite fundamentally requires intense heat to exist. Once you flash freeze it, the lattice slams shut, and it is forced to transform into other things.
Right.
The entire puzzle for the engineers is controlling what it transforms into. And that brings us to the second phase we see on the X-ray, which is ferrite, tagged as SVAR34.
Ferrite is the villain of our cooking show, right? The soft stuff.
Ferrite is a very soft, weak crystal structure. It lacks the carbon reinforcement we need for strength. And when we examine the simulation data, we see that ferrite stubbornly hides out in the thick, bulky ends of our 3-degree gear slice.
Okay.
It reaches a volume fraction of 0.384 in those specific areas.
Why is it only hiding in the thick ends?
It comes down to surface area to volume ratio. The thick ends have more mass, which means they physically hold onto their heat longer during the gas blast.
Right, they don't chill as fast.
Exactly. They cool down just a fraction of a second slower than the thin parts of the slice. But that tiny delay gives the metal just enough time for the soft ferrite phase to form.
And we don't want that.
No, we definitely do not want this weak stuff anywhere near the critical stress zones of our gear teeth.
Which sets the stage for the absolute star of the recipe, perlite, labeled as SVAR47. Perlite is the layered, tough-as-nails structure we are desperately trying to achieve.
If we connect this to the bigger picture, the entire high-pressure gas quenching process, calculating the exact pressure, speed, and flow of that cooling gas, is meticulously timed to bypass the temperature zone where soft ferrite forms in the critical areas.
Oh, so they're trying to dodge it completely.
Exactly. The goal of the supercomputer simulation is to find the exact cooling curve that forces the hot austenite to skip right past ferrite and transform directly into perlite.
And what makes perlite so special?
Perlite is unique because it forces the iron and carbon to arrange themselves into alternating microscopic layers. It's almost like a sheet of metallic plywood, giving it immense toughness.
Looking at the simulation results, it worked beautifully. Perlite dominates almost the entire slice, hitting a maximum volume fraction of 0.993. That is over 99% pure, tough perlite in the most critical zones of the gear tooth.
The simulation proves their timing for the flash freeze is highly accurate. They have successfully trapped the carbon inside the lattice, creating massive internal tension, and locked it into a very durable configuration.
Okay, so we've prepped the digital mesh, marinated the steel in carbon at 950 degrees, and flash froze it to lock in 99% perlite. It sounds ready to me. But before anyone puts this in a real transmission, there is one final exam, the ultimate taste test.
We need to grade the final hardness of the entire structure.
Right.
To do this, the engineers take the phase transformation data from Dante and couple it back into Ansys to evaluate a metric called total hardness, which the software labels SVAR2.
This gives us a literal scorecard for every microscopic point on the gear. Looking at the center connector first, the thin central bridge of our gear slice, this is the crucial connector of our piece. The scorecard shows it hits a peak hardness score of 36.809.
And a score of 36.809 indicates a highly successful material state.
Awesome.
Being a thinner section of the geometry, it cooled rapidly enough to maximize that tough perlite transformation we just talked about. It is solid, durable, and ready to handle the friction of the highway.
But then we look at the thick, bulky ends of the gear slice. Their hardness score plummets. They lag behind at a much softer score of 16.423.
Right. Because those bulky ends retain their heat longer, the cooling rate slowed down.
The delay again.
Exactly. That allowed the pesky soft ferrite to grow in those specific regions, which fundamentally compromised mechanical hardness at the ends of the slice.
So what does this all mean? We went through all this effort, tapped into supercomputers, meticulously controlled the carbon and the gas blast, and the ends of our gears still came out soft at a 16.423. Doesn't that mean the recipe failed?
Actually, it means the simulation was a complete success.
Really? How so?
The data here is flawless because it is telling the engineers the unvarnished truth about the physics. It shows them, with millimeter precision, exactly where the gear is bulletproof, that central bridge, and exactly where it is critically vulnerable.
Oh, I see. It is predicting the exact physical location where the gear would eventually break if they manufactured it using this current design.
Yes, if they skipped the simulation, poured the physical steel, and put it in a car, that soft end with a 16.423 score is exactly where the clunk would happen on the highway.
That's terrifying.
It is. But because Dante and Ansys caught it in the virtual kitchen, the engineers can now make a quick, cheap design tweak.
How do they fix a localized soft spot like that? Do they, change the gas flow?
They have a few options. They could change the physical geometry of the thick ends to thin them out, giving them a better surface area to volume ratio so they'd cool faster.
Okay, that makes sense.
Or, as you suggested, they could adjust the CFD parameters to focus a heavier blast of cooling gas directly onto those thick ends during the crunch.
Ah.
They can iterate these changes in the software in a matter of hours and completely fix the failure before it ever exists in the real world.
That really drives home why this deep dive matters to you, the listener. We merge onto the highway every day, totally trusting our machines. And the only reason we can do that safely is because modern engineering is essentially highly accurate, very expensive virtual cooking.
It really is. It requires the right raw ingredients, a finely tuned 950-degree oven, a supercomputer to run the recipe, and the exact knowledge of when and how fast to chill the metal down to bend the physics of iron to our will.
By running these virtual simulations, material science is genuinely saving lives. It prevents catastrophic, clunky breakdowns, keeps you safe when you're pushing 70 miles per hour, and saves manufacturers millions of dollars in physical testing.
Right, they don't have to build and break 50 real gears to find the perfect one.
Exactly. They just cook it perfectly in the software until the data is pristine.
This raises an important question, though. We just spent this entire deep dive uncovering the extreme molecular trial by fire required to perfect just one single simplified slice of a gear tooth.
Yeah, just one little 3-degree slice. And a modern car transmission alone has dozens of these gears, and a standard car is made up of over 30,000 individual parts.
Exactly. So as you're driving to work tomorrow, listening to the engine hum smoothly along, leave yourself pondering this. What other invisible high-stakes recipes are keeping your car's engine alive and purring right now?